For those of you may not know me, I'm Catherine Donnelly. I'm the director of the Health Services and Policy Research Institute. And we've had these now for just over a year. Our new, I guess last year, 2024 was our first kickoff. So this is our 1-year anniversary talk, which is super. So happy to have Jonas Shellenberger here today. So he has an interesting background, which brings both a clinical lens and a research lens. So Jonas graduated as a respiratory therapist, and he worked as an NICU flight transporter for 9 years in the US before coming to Canada. I thought that was an interesting piece of tidbit, Jonas, and completed his MSc in Epi at Queen's University in 2021. And he has been an ICS analyst and is now a senior analytic epidemiologist at ICS Queen's here. And it's great to have you, Jonas. This is your second Methods Monday talk. And today you are going to be talking about interrupted time series and mediation analysis. And I'm extremely keen to hear about that. So I'm going to have to leave about 1:45, and Elliot's going to take over the reins, and we'll wrap up and monitor the chat and wrap up there. But before you get started, I just want to share my screen really quickly, because after Jonas, just for people to know, can everyone see that, Nicole? So we're shifting back and forth between quantitative and quantitative, but Nicole Babette will be talking about issues and strategies to manage authentic participation in qualitative research. And there's been some interesting work since COVID about participants or non-participants who are in qualitative, both interviews and surveys. So this will be a really interesting talk as well. But in the meantime, Jonas, I'm going to hand the reins over to you. Thank you.
Thank you very much for that introduction, Catherine. It's kind of funny. I don't often mention my clinical background, and yet you managed to tease that out. And well, there you go. Yes, I did in fact work in PICU and NICU for 9 years, including flight transport. Okay, so I'm pretty sure. Yep, I'll just get my PowerPoint up. I've got my script ready to go. Can everybody hear me? Great. And without much further ado, here we go. Let me just read from my script here. Hello, boys and girls. Today we are going to learn how to tell that. Oh, wait. I'm sorry, this is the wrong presentation. Hold on. There we go. Hello, everyone, and welcome to this presentation on interrupted time series analysis. I hope you find this presentation useful and informative. Now, before I begin, I'll give you a quick overview of what to expect in this presentation. I'll start by first describing what exactly a time series is and what the different components of it are. I'll then describe some of the techniques that I know of to analyze an interrupted time series, and then I'll finish with a walkthrough of how to go about analyzing one with a simulated case study. So without further ado, let's first go over what a time series actually is. So what is it? A time series, as its name implies, is a series of observations at different points in time. They can be either fixed frequency or irregular frequency, though typically we analyze fixed frequency time series, that is evenly spaced once per day or once per week, as long as it's on the same weekday and so on and so forth. And that specifically is what I'll be focusing on in this presentation. And as an example of what a time series might look like in raw data form, here you go. This is a very short fixed frequency time series showing age, sex, standardized incidence of some imaginary thing that I made up over, just for the purpose of an example, over the first 4 months of 2022. Now, there are 4 things that one frequently sees in a time series. These are non-stationarity, autocorrelation, seasonality, and noise. I will go into the first 3 in more depth, and for noise, I will simply say that that is random error that exists after you account for the above 3 components of the time series. And I should also mention that out of all 4 of these features, the one that I would expect to see no matter what is noise. Time series data very often has one or all of the other 3, but not always. But noise is there no matter what. So I'll start with non-stationarity, but to understand what non-stationarity is, because it can actually mean a couple of things, you must first understand what a stationary time series is. A stationary time series is any time series that is a horizontal constant mean with a fixed error term, which is also often known as a white noise process. And it looks like this. This is a stationary time series. There is random noise around a mean. There is also some cyclical variation that you can see if you look closely that isn't noise, hence the repetitive spikes. And actually, because of those, this is actually technically called a weakly stationary time series. A strictly stationary time series wouldn't have the spikes. The probability distribution of the different points would be independent of the shift in time. That's not really all that important to know. For the purpose of an interrupted time series analysis, that's not necessary. Weak stationarity such as this is enough to assume. So with that in mind, a non-stationary series has at least one thing that violates the stationary requirements that I mentioned before. These can be either a trend or also a heteroscedasticity, meaning the variation around the mean changes with time. So for example, here is a non-stationary series. You can see this upward trend in time very clearly. You don't even need statistics to tell you that. This isn't stationary. The mean is not constant. In fact, this is the exact same time series as the stationary one I showed you 2 slides ago, without the differencing needed to render it stationary. So moving on, autocorrelation. Unfortunately, that's not so easy for me to visualize, and the topic is a little bit more complex than what I've written here. For now, I will say that autocorrelation means that the value of the time series at some time t depends, to an extent, on what the value was at time t-1 or possibly earlier. Also, for now, I will say that there are specific plots used to assess autocorrelation and tests as well. I will go into more detail on that later. And finally, there is seasonality. Now, seasonality does not necessarily mean that something happens in a given season. It means that there is variation in the time series that occurs in a predictable fixed interval in a cyclical manner. A good example of this is monthly influenza prevalence. This would show seasonal variation in that prevalence is usually higher than average in the winter months. Weekly drug dispensings may show a similar cyclical pattern. Now, depending on the unit of time used, seasonality may, sorry, is there a question? No? Okay, I must be hearing things. Sorry about that. Now, depending on the unit of time used, seasonality may be more or less likely to be present. I would not be surprised to observe seasonality at any unit of time less than a year. For example, monthly time very frequently shows seasonality at the 12-month mark, meaning, the value of a time series 12 months from the current time is going to be similar to some extent to what it is now. Annual data or more coarse measurements of time, it's less likely to see seasonality. To observe seasonality with, for example, a time interval of a year, something would have to vary by some yearly multiple. And the only example I can think of actually really isn't medical. It's that if you were observing the adult cicada population, that would exhibit a 7-year seasonal variation pattern. But just to get you used to the idea of what a yearly seasonal pattern would look like, and just, that's the only thing I can think of. Well, okay, I guess number of Olympic athletes participating in a game, that would exhibit a 4-year cyclical pattern. So there you go. But that's what seasonality is, really. So you may be thinking this is all well and good so far, but I have yet to even mention what an interruption even is. In short, an interruption is an intervention of some sort. This effectively divides the time series into 2 different eras, pre and post-intervention. With population level data, this could be something like the start date of a new health policy. It could also be the publication of a new clinical practice guideline by a college of surgeons, for example. Or it could be something catastrophic, like a natural disaster, or the one that everyone's familiar with by now, the start of a pandemic. It is typically represented in the data as the date that the intervention took effect. Now, interrupted time series analysis is particularly concerned with exactly this kind of a situation, which leads me right into what is interrupted time series analysis. Interrupted time series analysis is a branch of analytical modeling techniques that descends actually from linear regression. In general, if you plan on doing an interrupted time series analysis, you are likely following what is known as a quasi-experimental study design paradigm. Now, the operating principle of this kind of study is that if an intervention happens uniformly at a single point in time to everyone in the study population all at once, and that the study population therefore does not substantially differ immediately pre and post intervention, then you can use the population before the intervention as the control group for the population after the intervention, and you have basically gotten as close to a randomized control trial as you can get without actually conducting such a study. And here is just such an example of a quasi-experimental design taken from a study that was actually done at ICES. Now, this study looked at timely follow-up with a colonoscopy in response to a positive fecal occult blood test. Long story short, a positive fecal occult blood test can indicate possible colon cancer, hence you need a colonoscopy to confirm that. Now, the graph here actually shows what the average rate of colonoscopy uptake from a positive FOBT was month over month. Beginning in February 2010, the vertical green line, Ontario revised the standardized notification to a patient's primary care provider to explicitly state what a positive FOBT indicated and to strongly recommend a follow-up with a colonoscopy. Now, starting in October 2010, the red line, Ontario decided to then take things a step further and sent a letter to patients directly saying, hey, you had a positive FOBT, and we recommend a colonoscopy as follow-up. So think about this for a second. We have two interventions that happen uniformly at one point in time, well, 2 points in time, but 1 point per intervention, to the entire study population, thus allowing us to use the population before and after each intervention as a control group. This is a quasi-experimental study through and through. I should also mention that the results of this study were actually very interesting. The revised notification to PCPs didn't actually appreciably change the uptake rate, but the letter to patients did. You can see that right here, the rate of the slope of the line actually changes and becomes a good bit steeper. One other minor note, this study right here is a study that made me want to work at ICES. Back when I was doing my master's degree, it was a study. So.
Jonas, so sorry to interrupt you, but
Yes.
I'm seeing a little notification on your screen saying stop sharing, hide.
Thank you.
There we go. Just don't want to miss
Sorry,
any of your data.
Thank you, Sherry. I didn't see that. It was on my other screen. Okay, now there is a family of models that can handle the various components of a time series to some extent or another. Autoregressive models can deal with autoregression. Moving average models make an assumption that an observation is correlated with the error term, meaning the difference between what the observed, observation was and what its predicted value should have been. An integrated model, difference is a term which can deal with a trend to help stationarize a time series, or it can deal with seasonality. And then there's ARIMA models, which is a generalization of all of the above in one. And that in particular is what I'm going to focus on. But before I do, there is one very simple method that deserves an honorable mention. This can analyze an interrupted time series analysis as well. It's called segmented regression. It's very simple. It is a linear regression model that treats time itself as a predictor variable. Or also you can look at time since the intervention as well. That said, one of the fundamental assumptions of linear regression is independence of observations and normal distribution of error. And this is frequently not the case in time series analysis. Autocorrelation violates the independence assumption, and time series data frequently has a heteroscedastic error term, at least with untransformed data. Nonetheless, under certain circumstances, this actually can be used. And I should mention that this right here, if I'm not mistaken, that actually did use segmented regression. So just keep that in mind. It doesn't necessarily have to be ARIMA. This works too. And there are also other models that I'm not even mentioning in the study that can analyze this kind of data as well. Why am I not mentioning them? Well, because I don't really know them very well, and I don't think I'm qualified to talk about them. But for the purpose of interrupted time series analysis with an ARIMA model, I will carry on. Now, before we move forward, let's stop for a second again and go over a little terminology. You will hear me use the term lag a lot moving forward. So what's a lag? A lag at n is the observation n time periods ago. Therefore, lag 1 is the immediate prior lag. It's the observation at t-1. Lag 2 is the observation at t-2. Lag 3 is the observation at t-3, and so on and so forth. And I'm also going to give you a very simple overview of the 3 basic intervention forms that you can see in an interrupted time series analysis, as well as a graphical representation. A pulse is a little quick blip that is not permanent. A shift is a permanent constant addition, and a ramp is, well, for lack of a better term or more precise definition, it's a ramp. The magnitude of the effect increases as time goes on. Now, there are some requirements with regard to the minimum number of observations. For an overall time series, various sources give various numbers of observations needed to analyze a time series, but a commonly cited rule of thumb is 50 observations total as a minimum. Further, you need a number of time points before and after the intervention before you can reliably detect whether the intervention had any effect. In other words, you have to be able to establish what the time series trend was at baseline, and you have to be able to establish whether there was a difference after the intervention. How many observations that is, I can't give you any actual number here. It really depends on how strong the intervention's effect was. I can say that the weaker the effect was, the more observations you'll need to be able to tell. So now that we've got a description of what an interrupted time series is, I will provide a walkthrough of how you go around actually fitting an alignment model with a hypothetical scenario. Here's the idea. We are now in a parallel universe where the requirements for school-aged children to be vaccinated against pertussis were relaxed in mid-2008. We aim to assess the effect of this relaxation of the rules by looking at the pertussis incidence rate before and after the rules were changed. Just to be extra upfront, I did not use real data for this walkthrough. This is all simulated data. So don't worry, I'm not violating any privacy or anything like that. This is all fake. So the very first thing that you should do with any time series is plot it. This seems pretty self-explanatory, but it's worth mentioning that visual inspection alone can tell you a lot about what you may expect to have to do. And wow, what a mess we have here. Just from this plot alone, one can see that this is not stationary data for 2 reasons. There is a trend that at least starts midway through the data, right about here. And the error term is definitely heteroscedastic over time. It's pretty constant right up to, visually anyway, about here, and then it starts jumping all over the place and seems to get bigger and bigger as time goes on. Also, does the intervention have an effect or not? That's a good question. This is not clear from looking at it. There is definitely a bird's eye view uptick at some point after the intervention, but whether it did anything immediate is kind of hard to see. Okay, now that's much better. The second step is to stabilize the variance, and often you do that by log transforming the data, as I have done here. So this is now the same data, log transformed, same plot. There is very clearly still a trend of the data. The variance seems a lot more homoscedastic over time, and that intervention also looks a lot more promising. Suddenly you can see that trend start to occur, much sooner after the intervention actually happened. And this is actually a less smooth curve, so indeed it may have actually immediately started, and the curve wouldn't have necessarily shown it immediately. So anyway, so far so good. We've stabilized it. We need to actually fit the model first. So the next step in the model fitting process is to determine both whether we need to difference the series and where. Differencing means subtracting the current value in time from another value that occurred before it. So a lag 1 difference means you're now analyzing what is the difference between the current point in time and what it was at the immediately preceding observation. So whether we need to difference at all, we can do this by assessing the autocorrelation function plot. We can also use unit root tests, such as the ones mentioned here, to assess if a series is stationary out to a given number of lags. I usually look out to 24 lags, but there is no rule of thumb here that I am aware of anyway. Now, we already saw the trend ourselves, so we know that we need to difference at least at lag 1. That is how you deal with a trend. You start by differencing at lag 1. That gets rid of the trend. But sometimes you need to difference out further than that. And how do we tell? Well, since I use SAS, I get this nice plot that tells me the difference. But, well, where? Let's take a closer look at 2 of those plots. The autocorrelation function plot, which I will call the ACF, and the PACF for partial autocorrelation function plot. So this is the ACF, and it tells us how much each observation is correlated out to 24 lags. As you can see, each observation is in fact very strongly autocorrelated with prior observations. Lag 0, the autocorrelation is going to be 1, and it always will. And one observation at a time is always 100% correlated with itself. Lag 1, that looks to be between 75 and 80% correlated with this lag right here at lag 0. Lag 2, still pretty strongly autocorrelated, and it continues to be a statistically significant autocorrelation out to, about lag 8 or so. Note the very general gradual decline. This is indicative that there is a trend and that we should difference. Now that said, we already knew that much just by looking at the plot. So far, okay, not really a whole lot of help, but it does confirm what we pretty much already knew. Now this is where the partial autocorrelation function plot comes in. This shows the autocorrelation with prior lags after you take the autocorrelation from all lags between the current observation and lag n away. Now what this tells us is that the first observation is in fact somewhat strongly autocorrelated with lag 1. That shouldn't change between the ACF and the PACF. Lag 2 is still got somewhat of an autocorrelation with the current observation, but not anywhere near as much once we take away the autocorrelation due to this observation here. Lag 3, still a little bit, still just over statistical significance, but anything beyond lag 3 is no longer statistically significant. So in this case, we actually have a judgment call to make. One could try to difference out to lag 3 and have some justification in doing so. However, whenever I see a partial autocorrelation less than 0.5 or so, I've had good luck with differencing at the prior lag. Now, in this case, that would be differencing at lag 1. Then there's also brute forcing it, which is try differencing at lag 1, at lag 2, and at lag 3 separate times, and take the difference that results in the different series with the lowest standard deviation. I have certainly done that in the past. Now, I'm not going to do that because I have an advantage that doesn't occur in the real world. I simulated the data myself. So I know where the correct place to difference already is, and it's at lag 1. Here is the plot that Prochlorima spits out after we difference at lag 1. The upper left panel in particular is what we are interested in here. It looks stationary to me, or at least stationary enough to analyze, though there are definitely some outliers near lags 20 and lag 40. Like those I would call outliers, but overall the rest of it looks pretty good. The mean is around 0. Doesn't appear to be a trend, or at least not one that I can easily see. Variance seems to be about constant, more or less. To confirm, we have a nice table of the ADF unit root tests, which do in fact show some statistically significant results, which is what you want to see. It's not conclusive though. And in this case, we also have the prior plots that do suggest stationarity, and we also have an intervention in the data that we suspect might result in an increased rate. This has not yet been accounted for. So it makes sense that the longer term lags don't show statistically significant results for stationarity. So this is an example of don't let perfect get in the way of good enough. Arima fitting is as much an art as a science, and we can definitely proceed with the next step and assume that this series is stationarized enough for us to proceed. So the next step to the model fitting process is to assess what autoregressive and moving average terms we need to add. We also should assess for seasonality. If there is a seasonal component, we will have to address it as well. So let's return to this plot. This time we're going to look at a couple of other panels. First, I can now assess for seasonality using these plots, and I don't see any. This is monthly data, and usually if there is a seasonal pattern, one would see a spike in both the ACF and the PACF plots at about lag 12, and there isn't one. We don't have that. In fact, once we look past lags 1 and 2, we don't really have any spikes whatsoever. Now, if we did, we would difference a second time at the seasonal lag, then we would have what is known as a seasonal Arima model. Is the lack of seasonality realistic given that we're looking at pertussis cases? Honestly, no, probably not. I would expect to see a seasonal difference when examining most respiratory infectious diseases, especially in children. However, for the sake of a simple walkthrough, I elected to ignore this fact and to just focus on a simple non-seasonal model. As for identifying what AR and MA terms to add, there is actually something specific about this set of plots. The ACF has a sinusoidal pattern, and the PACF has negative partial autocorrelations out to lag 2. Now, in Arima models, there are certain types of models that have known signatures, and this right here, these two combined, is one of them. This is known as a moving average signature. That is to say, the value at a given point in time depends to some extent on prior observations residuals, not their actual values. If it depends on past values as opposed to residuals, then that's an autoregressive model, which has a different signature pattern. Now, if a known signature pattern doesn't appear, which sadly happens pretty often, one can use the following guideline to decide which term to add. I'll leave the language up on the slide for you guys to peruse later, either by getting the PowerPoint presentation in your email or rewatching this on YouTube if you ever need it. In this case, the ACF does indeed display a sharp cutoff at lag 1, and lag 1 of the PACF is negative. This tells me we need to add a moving average term at lag 1. We now have an integrated moving average model. And this is what the resulting residual diagnostic panel looks like. Our ACF plots only show autocorrelation at lag 0, which should always be the case. And look at our white noise probability plot. None of those lags are statistically significant. We now have reduced the model to what is known as a white noise process. Any remaining autocorrelation is indistinguishable from random error. This does not always happen before we evaluate interventions. That depends on whether the intervention has an effect and how strong it is and how early in the series it happens. In our case, the intervention doesn't happen until month 41. So no small wonder that we don't see anything out to lag 24. In the real world, I would want to run the model again and look out a bit further. But since I simulated this data myself, I can confirm that the general form has been correctly entered at this point. So no need to bore you guys with additional residual diagnostic plots. I also won't go into seasonal OREMA model notation since it doesn't really apply, and I don't want to needlessly complicate things. There will be a slide of references at the end that point to several resources that go into so much detail about this process that it is infeasible to stick it all into a single presentation. However, I will mention that we now have fed a model that is called a 0-1-1 OREMA model. That is, it's a non-seasonal OREMA with P equals 0, no autoregressive terms, D equals 1, difference at lag 1, and Q equals 1, moving average at lag 1. And the model form, or the model equation, looks like this. Value at time t is equal to the average plus the value at t minus 1 minus a constant times the error term at time t minus 1. Now, since we have a constant in the model, this is known as a simple exponential smoothing with growth. So now we're at the fun part. We've made the series stationary. We've identified its general form. Now we get to see whether our intervention had an effect or not and what it was. I'll mention again that there are several different types of interventions that one can evaluate: a pulse, a shift, and a ramp. We can also do something called backshift transforming if we expect, for example, a shift with a gradual buildup to full effect, or a pulse that gradually decayed back to baseline instead of immediately going back down. I won't go into those here, but again, see the reference slide for more details. It can get pretty into the weeds, and I've already given you guys a whole lot of detail about this. So the form of the intervention is actually decided in the input data set, or at least it is in SAS and Python, the two that I'm methods, or the two statistical programming languages that I'm most used to. Okay, Python isn't a statistical programming language, it's a general one, but it's often used in statistics, but I digress. In this example, we have 3 interventions at time 2. The pulse is a 1 if and only if the time is 2. It's a 0 otherwise. The shift is a 1 starting at time 2 and at all points in time thereafter. A ramp is a 1 at time 2 and increases by 1 at each subsequent time point. Now, be careful. How to interpret each intervention depends on if your series is differenced or not. In this case, we have a difference at lag 1. Once we rearrange the equation, we can see that the mean is basically the difference between this month and last month's rate, minus an offset for how far off last month's rate was versus what it was predicted to be. In other words, whatever intervention we look at reflects how steep the trend line is. It is now a slope problem. In non-difference data, interventions are interpreted as impacting the exact mean rate over time. That is how far the line is from the x-axis. You can do this in difference data as well by differencing the intervention itself, but I'm not going to go into how to do that here. Again, needlessly complicated. There are a lot of different things you can do in OREMA models. I will just leave it at that. So in the real world, I usually evaluate all 3 different kinds of interventions and some simple backshift transformations of both step and pulse functions, just for the sake of being thorough about it. In this example, I'm going to step in and say, just try a shift. Trust me. Lo and behold, we have a significant trend regressor right here. And we can say with confidence that the intervention resulted in a permanent increase in the mean month-over-month increase of the log transformed rate by about 0.12. Note also that the estimate for the mean, which is mu, is both tiny and statistically insignificant. This implies that the average slope of the line was indistinguishable from 0 before the intervention was implemented. In other words, we had no average change in log rate until the intervention changed, and it resulted in a permanent change. Finally, we assess how well our model fits. This actually looks pretty good to me. We have normally distributed residuals, a little bit of deviation from the QQ plot, but not really enough to write home about, I would say. We could, in theory, use an outlier detection method and deal with a few of these outliers here, but I don't really think we need to. To me, I would say this is probably fine as is. And the last thing that we can do, which is optional, is we can run a forecast. Now, forecasting is usually something done in ARIMA models for economic and business data, but there really isn't any reason we can't run it with health services data as well. In this case, let's forecast what we can expect to happen to the rate in the next couple of years. Let's give the Ministry of Health something new to think about. Sorry. Here we see what is forecast to happen if we do nothing to change the intervention in green, or if we reverse the intervention in blue, meaning this is what happens if we continue to not mandate pertussis vaccinations to school-age children. This is what happens if we reintroduce the mandate. But wait a second, this is still log transformed data. Doesn't the actual non-transformed data make a bit more sense to look at? Oh, you bet it does. This tells a much more compelling story. You'll see a gradual return to baseline if you reverse the intervention and exponential growth if you don't. Okay, so time to wrap it up with a few software options, some references, and some time for questions. The first software package I'll mention is SAS, which is what I use to create the walkthrough for this presentation. Proc time series is great for generating seasonal decompositions and zoomed in plots of ACFs and PACFs. Proc SGplot was what I used for actually plotting the interventions at the beginning and the forecast plots at the end. And Proc ARIMA is what I use for the actual model fitting and the running of the forecasts. R has several packages, actually a lot more than I put here. I don't know that a truly comprehensive list of all of the R packages out there actually exists, but suffice to say that these three got mentioned a lot when I was doing a little bit of a background searching on it. I will say up front that I have never worked with any of these, but I'll go ahead and mention them here anyway. Python also has some software options, and bluntly, I find it very easy to use. Plus, like R, it's free. Beware though, the documentation for Python is not anywhere near as complete as for either SAS or R. So, just make sure you have some other references at hand so you have a good idea of what you're doing. There are also options that I've heard of in Stata and SPSS as well. In other words, if you have access to any major statistical package, chances are you can run an ARIMA model. Here are 3 methodological references that I've relied on in the past, and the citation for the example time series study right here. In particular, for a methodology guide, I recommend the very last one from Duke University. It is the most art versus science tutorial I've ever been able to find, and it has been an absolute godsend in real world work. And with all that said, questions?
Thank you, Jonas. That was impressive. I'm just picking up one question in the chat. I have a few myself, but Oz, you had a question around log transformation. I had a similar one. I don't know if you want to ask that of Jonas.
Yes, thank you, Jonas. That was excellent talk. We learned a lot. Can you comment on the decision to log transform your data?
It was to stabilize the variance. If you go back, actually, I think do I still have my presentation up? I think I still do. Yeah, so if you go back over here, way back, that was meant to actually stabilize the variance over time specifically. So remember, one of the things that you need to analyze a time series is that you need to stationarize the data. You need to make sure that you have a constant mean, and you need to make sure that the variance is constant. And if you look, you can see the variance is definitely not constant over time. Very little variance here, and suddenly it starts jumping all over the map the further out you get. Once you log transform it, you no longer have that problem with the variance. Sure, there's some wandering, but the actual variance from the mean it's close enough to constant that we can actually analyze it. That's why we log transformed it.
Okay.
That won't always stabilize. That won't always stabilize your variance, but it's always a pretty good first step.
And if I can have another question, Jonas, with the many interventions, we expect some lag in when the effect is seen and that period of adoption. How do you incorporate that in your analysis?
That is a great question, and I'm glad you asked it. Remember when I mentioned backshift transformations? That is how you do it. A backshift transformation means that you're no longer necessarily assuming that it happens uniformly at one point in time. A backshift transformation of a shift, for example, assumes that, yes, you do have a permanent increase, but say month 1, it's not all the way up to maximum effect yet. It assumes that. There is a way to backshift transform a pulse in a similar but kind of reverse fashion. You can say, yes, we had an effect immediately, and it did eventually go back to baseline, but it didn't just immediately drop. It looked kind of like this. Thanks for asking that. That was actually something that I personally have run into in one of the studies I've worked on.
And do you ever do it on trial and error? Because we know it takes time to implement. We just don't know exactly when will that happen.
Yes. Thank you again for asking that. Yes, ARIMA models are very trial and error intensive. In fact, out of all of the different models and other analytical techniques that I've worked with, there are 2 that are very, very finicky, that require a lot of trial and error, a lot of go back, look at it again, try a whole bunch of different things. And ARIMA models are one of them. They are very, very hands-on. They require you to, it's a very high-powered tool, but it's like a chainsaw. You need to know what you're doing, or you're just going to end up creating a big mess all over the place. I should also mention that something that does happen with ARIMA models is you can end up with 2 different models that fit the data equally well. And it's really up to you to decide which one's the best one. The rule of thumb is pick the simpler one. But yeah, thanks for asking that too. Yes, it's very trial and error.
Thanks for those questions. I had a few too. Unfortunately, I have to leave before I probably get all my questions in. You talked about forecasting at the end. I guess I had 2 questions as well. Yeah. Just even from like writing a grant up, if a lot is trial and error, how do you write the methods up for a study with times like such as this? Like, how, from a reviewer perspective, like, will they require certain things in place, or what are your thoughts on that?
That's a very good question. Truth be told, I've never been on a grant application that involved a time series. What I would say is that we will evaluate trends in, say, for example, the age, sex, standardized rate of such and such a thing over time. Using an ARIMA model, we will evaluate autoregressive and moving average terms and backshift transformations of an intervention defined as the date that such and such a thing happened as appropriate. We will choose the model that results in the lowest standard deviation, and in the event that we have more than one model that works, we will choose the simpler one. We will also assess autocorrelation and partial autocorrelation functions to assess for seasonality and difference as appropriate. I would say that.
Which, what I just think, just what you said, Jonas, I think this is the value of having like an epi consultation in terms of, when you're thinking about writing a grant, because you might come up with a whole different sort of way of approaching it. And, just even what you said to capture that, I mean, you can see the value of having that lens. I was so intrigued with your forecasting, and you talked about that being done a lot in finances and not as much in health. I was going to ask you, do you have an example of a forecasting paper? I would love to read one. And just, is that something that you think people should routinely do if they're doing time series?
I actually don't have an example of forecasting with health data. Long story short, I ran out of time when I was making my my PowerPoint, and that was kind of low on my priority list. I know about forecasting mostly because I've taken a course on along with Manager Bua actually about machine learning and a whole bunch of stuff in Python, and that approaches it from a business perspective, and they go into a lot of depth about forecasting. With regard to forecasting with health data, I would say I think it kind of depends. The thing about forecasting is the further out from time zero you get, the less and less and less that assumption that the study population is the same as what your population at time zero is, the less and less and less that holds. So be careful about doing it. If you're looking at it 2 or 3 weeks out, okay, fine. If you're looking at it 10 years out, I wouldn't believe it. At 10 years, a whole lot of things can happen. I don't think anybody who was making a forecast in January 2019 would have expected that in 2 years' time, everybody would be staying at home and going nowhere, for example. And things change.
That's great. Thanks, Jonas. I'm going to have to slip out now for class, but I just want to say how greatly appreciative I am, all the work you put into it and just how interesting that was. I'll pass it over to Elliot.
Sure.
Thanks, Catherine. Yeah, Jonas, I just want to follow up on the forecasting because I see it very seldomly within our health admin data, but I'm just wondering, like, how much extra work is it to do that, to add it on to your existing analyses? Is it a lot of work? Is it a heavy ask for the analyst to do?
No, it's a single line of code in Procurima.
Okay.
I mean, it may be a bit of work if you've never done it before. Truth be told, it took me probably about a half hour of poking at Procurima until I finally figured out how to do it. But once no, it's not a big ask at all.
Wow, that's fascinating because I know policy people would love to see even projected out 1 or 2 years, but we never do it.
Yep.
Yeah. Vic.
Yeah, Jonas, brilliant. Thank you so much. I did this stuff 40 years ago, and it's changed so much. I think with forecasting, you just have to be very careful that you consult somebody like Jonas in the sense that it's the interpretation. You get a whole bunch of statistics. The code is easy. There's no doubt about it. And some of them do it automatically with regression and stuff like that. But it's the interpretation. One thing you said that really that hit me and has hit me in the butt when I've done it before. It's the longer you go out, the more time you go out, it is very hard to be accurate. It's like the weather.
Yep.
Right? A day is fine, 2 weeks is not. And there is always a confidence interval around that, and you can see visually how the confidence gets wider and wider as you go out in time. So it's just to be cognizant of that and consult with a person like you is very important, especially in a grant proposal, because there's always some guy or some person who's an expert on projections, and they'll get you every time, and you don't want that to be the one thing that they can say no on. So, well done.
Anyway. I'm glad you mentioned the uncertainty as time goes on. I actually left the confidence bands off of that plot because, especially with the untransformed data, once you get out past about a year or so, it's so wide that it's like, oh, okay, this is busy, and I can't really even tell what's going on with this.
Great, Jonas. I don't see anybody on the chat. I had a couple questions, Jonas.
Sure.
So, I mean, the way you were data visualizing the interrupted time series, you were using some line and some bar graphs. We're always looking for different ways to represent the data to make it impactful. Any other suggested visualization techniques, or what's really, how do you represent this data really impactful?
Well, I think it depends on what aspect of the time series you mean to show. If you want to show what the actual rate was over time, a line plot is your friend. It really is. It tells you a lot. You can show bars underneath if you want to show counts of it. I wouldn't do that by default. The study that I showed that had the bar graphs was done, before I was even an epidemiology student. So I can't comment on why exactly that was done. It might have been a journal request. I don't know. In terms of the autocorrelation function plots, I'm mostly showing this from the perspective of an analyst trying to figure out what the right thing to do is. And in that case, I wouldn't recommend straying away from it. I found that it's kind of, it hits the happy medium of not trying to do too much with it. Or too much more, or like, how do you fix a mousetrap, right? If it works, don't fix it. In terms of if you're trying to visualize how the magnitude of the actual effect itself, I mean, kind of comes down to how strong the effect is. I mean, you can tell pretty easily with the log transform data that there is an effect pretty much as soon as you institute the intervention. The untransformed data, I think, does a better job of showing how big of a problem it actually is, though, as opposed to, did this have an effect versus how big is the actual problem. So if it were me, I would produce both plots and submit both to a journal. And if they don't want one, then okay, we'll take it out. But yeah, that's a good question. In terms of how else to show a time series, I honestly hadn't really thought of it much further beyond that. Do you have any ideas?
No, that's great. I've seen sometimes it represented in a scatter plot with all the points projected over time. That's kind of interesting. You get both the magnitude and the slope in one. You certainly could do it with a scatter plot. And actually, when I was first putting this all together, that was my very, very first plot that I created. I added the line because it's a time series. As you go in time, it just zigzags all over the place, and it shows you what the next order of sequences is. Especially when you have a lot of time points. If you get too many clustered into a space in a graph, it gets kind of hard to tell which is which. But if it's nice spaced out, then I would say a scatter plot will probably work just fine. Yeah, great.
I do like less smooth curves also. It just really, really helps, I think, find what the actual average is over time.
Right.
Also, vertical lines to show when the intervention happens. That I would consider that yes, you should have that no matter what.
Yeah. You did a really good job of simplifying it. Like oftentimes it's a complicated analytical approach and you lose people. This is more of a pragmatic question I have. Oftentimes the resources are analysts, and I'm just wondering from an analyst perspective, where does this fall in terms of, is it labor intensive for the analyst to do interrupted time series? Or I guess it depends on the data, or can you just comment about, when is, like, obviously if you have unlimited resources, it's not an issue, but oftentimes that's not the case, right?
Well, the first question is, has this analyst ever done one before? Because if they haven't, it's gonna take a while. It took me quite some time the first time I learned.
Yeah, so that's the number one thing to factor into your decision, right?
So if you have limited funds, I would suggest requesting somebody who's done this before. And even if it's for someone who's done it before, I would consider this one of the more labor-intensive things one can do. Yes, a lot of it does come down to how clear-cut is it. If you have a nice simple thing that doesn't have a seasonal difference, that your outliers are few and far between, and it just neatly falls into place pretty much immediately, then arguably it's not that labor intensive. In the actual time series study that I've done, that was not the case at all. I ended up with I think 2 or 3 different models in a couple of situations, and ended up going with, okay, just go with the simplest one. And actually, that is something that running a forecast can help you with, actually. Not to present, but look at the forecast. If it looks nice and smooth and easy, chances are it's correct. If it suddenly looks like it just goes all over the place or just bounces off or falls off a cliff, there's a good chance there's something wonky with your model. Probably don't want to go with that one.
Right. Yeah.
Unless you would expect to see that happen, of course.
Yeah, that's great, Jonas. Really, really pragmatic things to consider when you're looking at interrupted time series. Anybody else on the call have any questions for Jonas?
Elliot, if you don't mind, I still have another one.
Oh yeah,
Jonas.
Yeah.
Can you comment on how to set up your data if you want to account for the seasonal variation, but also for the time when the intervention was implemented?
Yeah.
And part 2 of this question is that what if you have 2 interventions and sort of you want to know when was the most gain in
Sure.
outcome?
So there actually isn't anything special you have to do if there's seasonality. The same structure will work for both seasonal and non-seasonal data. That's all done in the actual model itself, not in the data set. You need to have one variable that shows what the point in time actually was. Whether that's weekly, monthly, annually, it doesn't matter. You need something that tells you what time you're looking at. You need to have a variable for the value itself that you're looking at. Whether untransformed, log transformed, or whatever you're going to do with it, you need that. For your intervention, I would recommend 3 forms always. You want 1 for a pulse, which is a 1 at the time of the intervention and a 0 otherwise. You want a shift, which is a 1 at time of intervention and all time subsequently. And you want a ramp, which is a 0 before the intervention, 1 at time of intervention, and it increases by 1 for each subsequent time point. So if you've got all of those in a data set, you are equipped to do pretty much everything you need to do. If you have 2 interventions, that's fine. You have another variable, you have another sequence of variables with that intervention right there. How do you determine which variable had the bigger effect? Well, the easy way is to say, look at what the actual coefficient from the regression model is for your intervention in question. But you have to keep one thing in mind too. Whatever your second intervention is going to be the change based off the change from whatever the baseline plus the change from the first intervention was. So keep in mind what that change is in reference to is going to be possibly somewhat different. Also, if your second intervention is near the end of the time series and you only have like 1 or 2 data points after, there's a very good chance that there was an effect, but you can't see it yet. So.
Thank you so much, Mr.
Yep. And also plot it. If you have a big one, you'll see it. I cannot emphasize that enough. Plot, 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 and plot. This is a very plottable thing, and it's one of the most valuable things you can do if you're going to look into this particular kind of study.
Yeah, that's an excellent recommend. I know that you're always wanting to see where your data falls right early on, right?
Yep.
Yeah. That's excellent. What a spectacular presentation, Jonas. So I'll give the audience one more opportunity to ask any questions of Jonas. Otherwise, we'll give you a few minutes back in your day. Jonas, thank you very much for presenting. That was absolutely stupendous. You keep this up, we'll have you back on a regular basis.
No problem.
Thank you, Jonas. I'll say bye to everybody.
Okay. Thank you, everyone, for coming.